is the lecture on the t-test for two independent samples. This is covering chapter 10. Hopefully after reading it, which you've already done, and then watching these slides, you'll be able to understand what an independent measures t-test is. You'll know how to test the difference between two populations or two treatments using this particular statistic and test. You'll be able to evaluate and report the magnitude of the difference in a couple different ways, and understand how to evaluate the underlying assumptions and what to do if those assumptions are violated. So far, we've talked about two different statistical tests, one sample z-test and a one sample t-test. And if you recall from many weeks ago now, the z-test is when we want to test whether our sample comes from a population that has a known mean and a known standard deviation, right? So it's kind of the most basic test we can do when we know the mean and standard deviation. When we do not know the standard deviation, but we want to know the same thing, does our sample come from a particular population, we can use the t-test statistic and the t-distribution. And that still allows us, like it says, to estimate the probability of obtaining a given sample from the given population, and we use the estimated standard error. So this brings us to independent measures design. So most research studies do compare two or more sets of data. The data can be two completely different independent participant groups, or it can be data from the same group. And so the first is called an independent measures design or between subjects design. And that's when each participant or subject is only assessed on any particular dependent variable one time. The second is called a within subjects or repeated measures design, and that's when each participant is assessed on the dependent variable more than one time. So this might help you kind of understand this a little bit better. So let's say we wanted to find out whether listening to music helped people study. And we were going to test whether listening to music with words or just instrumental music, which one of those treatment types helped learning or memory the most. A between subjects design would have one group of participants in level 1 and another group of participants in level 2. So they would have one set of participants, level 1, listen to music with lyrics, and then a separate set of participants listen to music without lyrics or just instrumental music. And you'll notice that Ross is only in level 1. He's not ever going to be tested on the other level of the dependent variable. He will only listen to the music with lyrics and then test the memory or study ability or whatever the dependent variable is going to be. And contrast that with the within subjects design, where you'll see that each person is listed twice. So Monica is going to listen to music with words and then maybe take a memory test. And then she will also listen to music without words and take a memory test. So she's going to be measured on that dependent variable of the memory test twice. Once listening to music with words and once listening to music without words, right? And so that would be called a within subjects design, where the participants are measured on the dependent variable more than one time. Again, the between subjects design, each participant is only measured one time. So this is, I think, a handy chart to come back to when you're trying to remember what the difference is or how each one of these. Okay, here's another graphic depiction of the independent measures research design. So in this graphic, what it's showing you is that there are two separate samples that are used to obtain information about two unknown populations or maybe treatment conditions, right? So in this case, perhaps the research question is, do social skills scores for children with behavioral difficulties taught by method A differ from the scores for children taught by method B? And so what we're wondering is, we're going to test each group of children. One group of children will be taught by method A only, and then the other will be taught by method B only. Two separate groups, no overlap in the participants, and we're going to measure the social skills scores for both groups. And then we're going to use the sample data to try to make inferences about the population. And in statistical terms, we're going to be looking at, are the two population means the same or different? So we'll take sample A and we'll measure the social skills scores, and sample B, measure the social skills scores, and then again, try to measure or assess, are those two means the same or different? And we'll use that to make inferences about whether the population means are the same or different. Okay. So real world example, kind of relating to love and puppies. So trying to give you a little dose of happiness here in the midst of our coronavirus pandemic. So this comes from a study by McNulty and colleagues. They examined across multiple universities, they examined whether directly altering affective or emotional associations involving a relationship partner could lead to changes in relationship status. So they asked a bunch of married couples to view a stream of images every 3 days for 6 weeks. And either participants were assigned to either the experimental group, where they viewed images of their partner with a positive stimulus, like puppies or sunsets, and then the control group saw images of their partner with neutral stimuli, like just a straw or a button, right? Nothing particularly warm and fuzzy. And then both groups completed measures that assessed their attitudes toward their partners and their marital satisfaction. And you might be surprised to know that the spouses who viewed their partner with positive stimuli had more positive partner attitudes and marital satisfaction than those who viewed the neutral images. So the two groups were different. They looked at the mean scores on those measures, and they were different, significantly different. So viewing pictures of your partner with the positive stimuli made a difference. So if you guys takeaway here, quick coronavirus takeaway, if you are feeling very frustrated by the people that you're currently residing with, since you're spending so much time together, maybe try looking at some pictures of them interspersed with pictures of really happy things, and seeing if that makes things a little bit better for you. Okay. Let's see. So another example of an independent measures design, do men and women have different attitudes toward gun control? So first, just to kind of review, what's the independent variable here? If we were in class, I would ask, just take a minute and think about whether or not you can identify what the independent variable would be and what is the dependent variable in this example. So the independent variable is gender. So whether you are male or female, and the dependent variable would be attitude toward gun control. And as it shows in this slide, we're looking at is the difference between sample means in the sample of men and the sample of women statistically significant. So recall that in hypothesis testing, one of the first things we're going to do is determine or state the hypotheses. there will be the null and the alternative hypothesis. The null hypothesis is that there is no difference in the population mean for sample 1 and sample 2. So the difference, if you took mean 1 minus mean 2, would be 0. The alternative is that there is a mean difference between the two. But remember or recall that if it's a one-tailed test, you're going to not just say that the two means are the same or different by saying either the difference will equal 0 or the difference will not equal 0. You're going to be more specific and say in the null hypothesis, the mean difference will be less than or equal to 0 or greater than or equal to 0, depending on which tail you're using. And the alternative hypothesis would be that the difference between the two means is greater than or less than 0, right? This is really similar to the Z and T test null and alternative hypothesis that we've gone over before. So you'll remember, here we go. Remember that the test statistic for the one sample t-test, we took the sample mean minus the population mean divided by the standard error. And in this case, we're going to be looking at the mean difference, right? So the difference between the two sample means minus the difference between the population means for the two groups, and then divided by the estimated standard error. And if you'll notice, remember the standard error is the standard error of the distribution of the mean difference. And we will go over how to calculate that in just a minute. The key here, when we're looking at the t-statistic for independent measures design, is to remember that it's the difference between the means. Okay, right, like I just said. Now we're talking about the differences between two groups. Okay, so the formula looks complicated, but if we break it down and kind of look more closely, the second part of the denominator under the null hypothesis is hypothesized to be 0, so we can get rid of it, right? So the sample mean difference, sorry, this should say the second part of the numerator. We're looking at the differences between the two sample means, right? The difference between the mean for group 1 and the mean for group 2. And then we're subtracting the difference in the population mean difference, right? So what's the population mean of group 1 minus the population mean of group 2? And according to the null hypothesis, if the null hypothesis is correct or true, the population means are not different, right? They would be the same. And so the difference between two means that are the same is 0. And so we can just get rid of that. The sample mean difference minus 0 is just the sample mean difference. And so the t-statistic formula becomes just the sample mean difference divided by the estimated standard error. And so in this case, the location of the mean difference obtained on the distribution of mean differences is what the t-statistic is. And what do we do about standard error? So let's go through an example and we'll answer these questions. So let's say you're interested, like I had on a previous slide, in studying whether men and women differ in their attitudes toward gun control. And so you survey a sample of 15 men in your first group and 15 women in your second group from Marquette asking them to respond to several questions about gun control. You come up with an attitude score for each person. You take the average of their responses across all items. Higher scores indicate more support for gun control. And so again, we're wondering, is there a significant difference between gender, between the two groups, a group of women and a group of men, in terms of gun control support? And so we'll conduct a two-tailed test because we don't know what direction the difference would be, right? We don't know if men would be more supportive of gun control or women would be more supportive of gun control. We just are hypothesizing that there will be a difference. And so it'll be a two-tailed test. The alpha is going to be set at 0.05. And so very first, we're going to compute the mean and standard deviation for each sample. So this is kind of what I'm calling pre-step number 1, calculate the mean and standard deviation for each sample. And I've listed those formulas for you here again. This is from way back in the beginning of class, right? The mean, sum of squares, which is then used to compute the standard deviation. You'll have these formulas on the exam, of course, and you should remember this from early on. So there's the computed means and standard deviations for each group. Now, step 1, we're going to state the hypotheses. So the null hypothesis is that the mean of the first group minus the mean of the second group is really 0, the difference between those two means, that there is no difference, right? The null hypothesis would say there's no difference between those groups. And so the mean minus the mean is 0. The alternative hypothesis would say that the difference, mean of group 1 minus mean of group 2, is not equal to 0, that there is some kind of difference, that the difference between the means is going to have some value indicating that those groups are not the same. So another way to say this, under the null hypothesis, we expect no difference between men and women's gun control attitudes, and that they come from the same population of gun control attitudes. And under the alternative hypothesis, we expect that there is a mean difference between men and women's gun control attitudes. So again, I'm just going to keep saying this. With this type of t-test, we are looking at whether there is a what is the average difference between these means. So we're creating a sampling distribution where if we took a sample of one group and a sample of another group, and we looked at the difference between the means, the calculated average of each group, we would find a difference, right? And we would plot that and do that over and over and over again. And so you'd have a sampling distribution of the average or mean difference between two group means. Step 2 is, again, to set the criteria for a decision, right? Set the alpha level. So we're still using the same t-tables that we used for chapter 9. Let's set the alpha at 0.05, and again, we're doing a two-tailed test in this example. What is the degrees of freedom? So for this kind of test, independent samples t-test, we're going to add our total n from both of the samples and subtract 2, because each sample has 1 degree of freedom. So we used to subtract just 1, but we have 2 different samples here. Each sample has 1 degree of freedom, and so we'll subtract 2. So degrees of freedom, in this example, we had 15 men and 15 women, and so it's 15 plus 15, so each sample size, minus 2, because you have 2 groups, and each group has 1 degree of freedom, and that's going to give us a total of 28. And if you look up in the t-table, the critical value for 0.05 two-tailed test with 28 degrees of freedom is going to be 2.048. And again, that could be positive or negative. And now we're ready to compute the test statistic. We still need standard error in order to compute the test statistic. So estimated standard error for an independent samples t-test It's going to estimate the average distance between the sample statistic and the population parameter. In other words, how much do we expect the sample mean difference? Again, we're looking at differences between two means. How much do we expect that difference to bounce around the population mean difference just because of sampling error, right? So we're looking at what's the standard error or the standard deviation on this sampling distribution of mean differences. And remember that if there is no difference between the two population means the samples come from, we would still expect some difference from the two samples taken since there is sampling error, right? So even if the population means are the same, the sample means are still going to have some variation because of sampling error, okay? Okay. So let's break this down because this formula, there's a lot going on here. We got the standard deviation over the sample size plus the standard deviation of the second group over the sample size of the second group, the square root of all of it. So let's start by looking at each sample separately, one at a time. So the standard deviation of the first group is variance over sample size, the square root of variance over sample size. Same with the second group. This tells us how much sampling error we expect in each sample, but we want to know the total amount of error involved in using two sample means to approximate two population means. And so what we will do is combine them. And when you rewrite it, you've got the standard error of differences, right? The mean 1 minus mean 2 is equal to the square root of standard deviation plus standard deviation. So let's do the computation here for this example. We already know standard deviation for both groups, 0.43 and 0.32. So this is pretty straightforward. We're just going to plug it into this formula. So our estimated standard error is equal to the square root of 0.43 squared over the sample size of group 1, which is 15, plus 0.32 squared, that's the standard deviation of the second group, divided by the sample size of the second group, which is 15. And when you do that computation, you get 0.138. And what this tells us is that even if there's no real difference between men and women in their attitudes, if there's no real difference between the means, their average attitudes, we can expect to see mean differences between the two samples vary by an average of 0.138 points. So one standard error or one standard deviation in that sampling distribution of differences of means is 0.138. So feel free to rewind and listen to that a few times and let that sink in, maybe pause and make sure you kind of understand that. Okay, now we are ready to compute the test statistic because we have all the pieces of this T test statistic formula. And remember, we have the mean of group 1, the mean of group 2, and the second part of that numerator there, the population mean 1 minus population mean 2, is based on what we hypothesize under the null. And again, that's going to be 0, right? So when we need to compute the T statistic here, we're just going to plug in these numbers that we've already found. So 6.23 minus 6.52, those are the sample means, minus 0. Because again, the population mean 1 minus population mean 2, if the hypothesis or the null hypothesis is correct, they will be 0. That difference will be 0. They will be the same. No difference. And then divided all of that, divided by the estimated standard error, which we just did on the previous slide, and we've calculated it to be 0.138. And so when you do that math, you get a t value of negative 2.10. So the next step is to make a decision on whether we reject or fail to reject the null hypothesis. So to decide that, we're going to look at t obtained. What is the t that we calculated? And from that, just that last slide, it's negative 2.10. And compare that with t critical, which was negative, remember positive or negative, 2.048. And the graph there of the distribution curve shows you t critical 2.048, t obtained 2.10. So that t obtained is less than the t critical. And so since that is the case, since our t obtained is in the yellow section of that tail, we will reject the null hypothesis and then conclude that men show significantly less support for gun control than women. And how you would report that is you would say T, parentheses 28, which represents degrees of freedom. The T, in this case, equals negative 2.10 with a p-value of less than 0.05. Now, new concept alert here. The last equation that we did first when we were looking at standard error, which is the denominator of the t-test statistic, we calculated standard error, but that's only going to work and be unbiased when the sample sizes are equal. So when the sample size of group 1 equals the sample size of group 2, you can compute standard error the way that we did, no problem. But what if the sample sizes are not equal, right? Let's say we sampled 17 men and 14 women. In that case, the error for the men needs to be weighted more heavily than the error for the women because the sample of men is larger, okay? And so this is corrected with something called pooled variance. And so it's the notation for pooled variance is S subscript P, S squared P. So it's the variance of the pooled variance. P is for pools, right? So pooled variance provides an unbiased basis for calculating the standard error. And there is the formula for pooled variance. Okay. Again, the pooled variance is obtained by averaging or pooling the two sample variances using a procedure that allows the bigger sample to carry more weight in determining the final value, which makes sense, right? If the variance for men is different than the variance for women, which they probably are, right, in most cases, and there are more men in the sample than women in their sample, then we want the variance for men to count more or to carry more weight. And so pooled variance will allow for that. Okay, why do we need to do this? Again, when the sample sizes are different, we can't treat the two sample variances as equal. When we're calculating the total variance or the average variance, if the sample sizes are different, we have to account for that. So, like I said, the formula looks a little scary, but just one at a time, plug in the values that we have and do your calculation. So when you break it down, it's not too scary. The important part, and what people usually have trouble with, is just remembering to use pooled variance in the first place. So when you're looking at an independent samples t-test, make sure you look at whether or not the two groups have an equal sample size or not. And if they do not, remember to use pooled variance. Okay. Okay, so let's calculate pooled variance with the example that we've been using with men and women in gun control. So even though in this case the sample sizes are equal, just for practice purposes and to kind of see what happens, let's go ahead and compute pooled variance. So to get the estimated standard error, first you're going to compute pooled variance. This is how you would do it if the sample sizes were not equal. So just pretend like they're not equal. You will see, I'm going to try using the pen here. So this formula is degrees of freedom times the variance for the first group. So let's measure effect size, right? This should be review. If the null hypothesis is rejected, the effect size should be determined by either using Cohen's d or R squared. Remember, an R squared is the percentage of variance explained. Here I've listed the formulas for both of these for you. So Cohen's d is estimated mean difference divided by the estimated standard deviation. And percentage of variance explained, or R squared, is T squared over T squared plus degrees of freedom. And when you do the calculations for Cohen's d, you're plugging in the mean of group 1 minus the mean of group 2 over pooled variance in this case. You get negative 0.76. We would report this as d equals 0.76, right? Absolute value, you don't need to use the negative sign. And how would we classify that effect size? I'll show you that in the next slide, just for review. What does it tell us? It tells us that men score 0.76 standard deviations lower on gun control support measure than women, right? So this is a good measure of, okay, there is an effect, there's a significant difference between men and women, but how big is that difference? And 0.76, how would we classify it? If you recall, here are kind of the rule of thumb for the value of D and how you would classify or categorize the effect size. So 0.76 is a pretty good sized medium effect, right? It's at the close to the upper boundary of a medium effect size. So maybe medium to medium large effect size in this case. So that's pretty good. And then percentage of variance explained. Again, there's the formula. Plug in our T obtained and the total degrees of freedom. So T obtained is negative 2.10. Our total degrees of freedom is 28. And you get 0.136. And you could say the interpretation of that would be 13.6% of the variability in support for gun control is due to gender. And if you recall, again, the rule of thumb or the conventions for R squared, 13 0.136 would be in the medium effect range. Okay, we can also compute confidence intervals. So you can calculate a confidence interval for estimating the population mean difference. So the sample mean difference is used to estimate the actual population mean difference, right? And so there's the formula to estimate population mean difference. We're going to use sample mean difference. And recall that the estimated confidence interval can provide an indication for the significance of the treatment effect. So if your confidence interval does not contain 0, the effect is significant. If the confidence interval does contain 0, then the effect is not significant. You fail to reject the null, right? Because the null would say that the population mean difference is equal to 0. And so if your confidence interval includes 0, meaning you're 95% sure that the actual difference between the means includes 0, then you do not reject the null hypothesis, right? And this makes sense because our confidence interval does not include 0, right? It was negative 0.57 to negative 0.01. And so we're 95% sure that the mean difference falls somewhere in that range that does not include 0. So likely this, as a result, this null hypothesis is likely not true. We can reject it. Okay, a few assumptions of the independent measures t-test. The observations within each sample must be independent. The two populations from which the samples are selected must be normal. And the two populations from which the samples are selected must have equal variances. This is the new one for this particular test. We haven't encountered this assumption before. This third assumption is referred to as homogeneity of variance. It's essentially saying that the variance of the first population should equal the variance of the second population. Homogeneity of variance is most important when there's a large discrepancy between the sample sizes. When the sample size is equal or close to equal, this assumption isn't as important, but it's still important. So if you have very different sample sizes, you really do need to pay a lot of attention to homogeneity of variance. So how do we test this? How do we know whether or not there's homogeneity of variance? There's a few ways. Excuse me. Okay. You can simply measure or compute if the larger sample variance is less than 3 or 4 times the smaller sample variance. So just look at what's the variance of the larger sample, and is that 3 or 4 times the variance of the smaller sample? So just kind of do basic math there. That would mean that there is no homogeneity of variance. And then there are 2 tests for this also, Hartley's Fmax test, which I'm not going to go into detail here. It's described in your book. And Levene's test, which you should be using in lab. We were not going to calculate it in this lecture, in this video, but I will show you briefly what that looks like. So Levene's test, again, used in SPSS, tests the assumption of homogeneity of variance. It's sort of a hypothesis test in and of itself. And so Levene's test is. So the null hypothesis is that the variance of the population are the same, which would mean there is homogeneity of variance. And the alternate hypothesis is that the variances of the population are not the same, right? And in this case, in the case of Levene's test, we want to fail to reject the null hypothesis, right? We're kind of hoping that the variances are the same. It's an assumption of independent samples t-testing. And so if they are the same, in this case, that's a good thing. And so failing to reject the null for Levene's test means that we can assume equal population variances. And again, that's what we're looking for. We are looking for homogeneity of variance. If we reject the null hypothesis and determine that the population variances are not equal, SPSS can still correct that for us, so we can still do our independent samples t-test. So it's not the end of the world, but this is definitely an assumption that you need to be aware of and you need to be checking. So Levine's test output from our in-class example. This is what it would look like in the SPSS output. And if you look at what I have, factors affecting the t statistic, difference between the two sample means. So this is repetitive information from previous chapters. The larger the mean difference, the more likely they are to come from two different populations, right? If it's 1.1 and 1.2, that's not a big difference between the sample means. If it's 1 and 10, that's a larger difference, right? So the difference between the two sample means is one factor affecting the t statistic. Also, sample variance. The lower the sample variance, the better the estimate of population variance. And lastly, sample size. And remember, just the law of large numbers tells us that the larger the sample, the better the approximation of population. And this is just showing you that variance issue. So when you have a high degree of variability or variance, it's harder to see the differences in two groups. So in the top, so we'll do one more example here. On the basis of her experience with clients, a clinical psychologist thinks that depression may decrease sleep. She decides to test this idea. Always a good thing. The sleep of 9 depressed patients and 8 normal controls is monitored for 3 nights. The average number of hours slept by each subject during the last 2 nights is shown in the table to the right. So is the clinician correct? Does depression decrease sleep? And so in this case, we can use a one-tailed test because we think that depressed patients will sleep less than normal controls. If we just thought they would be different, but we weren't sure whether depressed patients would sleep more or less, then we would use a two-tailed test. But in this case, we're hypothesizing for a specific reason that depressed patients sleep less than normal controls. And so we'll use a one-tailed test. And we'll set a significance value or alpha value at 0.05. And you'll notice in the table we've already calculated or computed the means for each group and some squares for each group. First, state the hypothesis. The null is going to say that when you subtract mean of population 1 mean of population 1 minus mean of population 2, that difference is going to be greater than or equal to 0. People with depression do not sleep less than people without depression. Is the way to interpret that. The notation for the alternative hypothesis is that mean 1 minus mean 2 is less than 0, right? That people with depression do sleep less than people without depression. So we should have a negative number here if the alternative hypothesis is correct, right? This hours slept of depressed people minus the hours slept of normal population should be a negative number. The decision criteria has already been set for us, 0.05. The degrees of freedom. I believe the depressed patients, there were 9, and the normal controls, there were 8. So 9 minus 1 plus 8 minus 1 equals total degrees of freedom of 15. And we looked up, if you look up T critical on the T tables, using degrees of freedom 15 and the alpha of 0.05 for a one-tailed test, you should see that T critical is negative 1.753, right? And it's negative, not positive or negative, because this is a one-tailed test. Okay, calculate the t-test statistic. Now first, remember, we're going to need to use pooled variance because our sample sizes are not equal. And so we'll calculate pooled variance using the formula, and it's plugging in the sum of squares numbers that we have and the degrees of freedom numbers that we have, and you get 0.217. Plug that into the formula for standard error of the mean difference. So as 217, I guess, if you're going to round. So we have our standard error of the mean difference. Let's put everything into our T formula. T equals mean of the first group minus mean of the second sample group minus population mean 1 minus population mean 2. And again, that. Now we're going to make a decision. Recall that we looked up in the T table, the T critical value for this is negative 1.753. We just computed T obtained and we calculated it to be negative 2.82. So here's what it would look like plotted on a graph. So T critical right here, negative 1.753, and here's our T obtained, negative 2.82. We're going to reject the null. People with depression sleep significantly fewer hours, and let's calculate effect size. Cohen's d, just plug in the formula, plug the numbers into the formula, the two means divided by standard deviation, which you're going to use pooled variance again here. You get negative 1.37. And you could interpret that by saying people with depression get 1.37 fewer standard deviations of sleep compared to normal controls. Another way to calculate effect size is to use R squared. Again, you're just plugging in numbers into the formula. Your T obtained and the degrees of freedom. And you compute an R squared to be 0.346, and you would interpret that by saying 34.6% of the variability in hours of sleep can be attributed to having a depression diagnosis. That's quite a lot of variability that is explained, right? Percentage of explained variability. So that would be considered a large effect size. And of course, we can also compute confidence intervals. So how about 95% confidence interval? Remember, critical values when you're doing confidence intervals are always two-tailed, right? Because we want to create a range. And so you have to use a T critical value for degrees of freedom 15, alpha 0.05 in a two-tailed test. So the T critical for that is plus or minus 2.131. Plug our numbers into this formula. So, okay. So normally I would ask if there are any questions. If you do have questions, I encourage you to rewind, watch the slide again. Definitely send me an email. Or maybe we can have some Zoom video conference calls. We'll get your questions answered. Okay, thanks.